Hello, my name is Abdel Zaro, and my research this summer is on scalable multi-robot motion planning. The main application of this research are automated warehouses where you will have robots moving shelves around to a station where the human will take the object off the shelf. The main motivation behind this research is that in these applications, there are many robots completing many different tasks, and they are all interacting with each other and the environment. So robots need to plan their motions in real time since there are so many robots and trajectories are constantly changing with environmental changes. And the current problem with current research is that the collision detection method that is used is inefficient and it limits scalability. So when you have systems with hundreds of robots, scalability is very important. Multi-robot motion planning is about generating these plans to get the robots from start to end goal without any collisions. Conflict-based search is a method used for multi-agent motion planning, and it's a two-level algorithm that plans paths that are collision-free for every robot. And the way it works is that on a low level, it generates trajectories for every robot individually, and on a high level, it looks at those trajectories and it checks for collisions. So my research specifically focuses on the collision detection aspect of conflict-based search. So it's about how can we generate and how can we detect future collisions efficiently. So if you look in this diagram over here, we want to be able to detect this future collision so we can set a constraint to prevent the robot from being at that location so we can prevent that collision from happening. So the problem with current collision detecting is that it's pairwise, which means that every robot has to check against every other robot. So for a few robots, it's not a big deal, but when you have hundreds of robots and you need to check every robot against every other one, it scales quadratically, which can be very computationally expensive. So imagine you had n number of robots, then the number of collision checks you need to do is n times n. So my idea was to implement quad trees, which are used in other fields, and tie them with conflict-based search to improve the collision detection method. And the way it works is if you imagine we have this rectangular space over here with two robots, A and B, and we're going to create a rule that says that we can only have two robots occupying a rectangular region at a given period of time. So in this next frame, we add a third robot, robot C. Now, because our rule said we can only have two robots per rectangle, we're going to partition the space into 4 different quadrants. And that's how it works visually, but the way the computer works with it is that it sees a tree. So whenever you partition the space into 4 new quadrants, it will create a new branch in the tree and it will store where every robot is in that tree. So this tree is helpful because it gives us a relationship between where every robot is relative to where the other robots are. And this is really helpful because now that we know which robots are near, we can do collision checks on only the robots that are near each other. So we will see this in the next frame. So imagine we add a robot E now to the area. Now a rule said that we can only have 2 robots occupying a space at a given time. So we're going to split the space once more and we create a new branch, as you can see over here in green. Now, the reason, as I mentioned, that quad trees are helpful is that it allows us to only do collision checks between robots that are within this green quadrant. So rather than doing collision checks between all the robots, you're only doing collision checks between the robots that are near each other. And while there's only 4 robots right now, if you had hundreds of robots and quad trees only allow you to focus on a small region of robots for collision detection, then it decreases the number of checks you have to do dramatically. And we will see that in these results. So the way we tested this is I created a Python simulation with robots placed in a circle that would swap positions. So as you can see in this picture, you have robots in a circle, and then they swap positions with every robot that is in front of it, and then it returns to the original configuration. So here are the results. And specifically, if you look at for the 100 robot system, for the number of pairwise collision checks that were required were 400,000, And for quad trees, it was only 2,000 approximately. And the reason that number is so different is because quad trees allowed us to only do collision checks on robots that are near each other. So we minimize the number of collision checks that we need to do. And the way the math behind this works is that for pairwise collision detection that's currently used, you need to do n times n number of collision checks. So if you had 100 robots, it's 100 times 100, and that's the number of collision checks you need to do. Conversely, for quad trees, it's n times log n, so it's not quadratic, and that's why you see so many less collision checks, and that's reflected in the time, where there's approximately a 4.5-second difference between the current pairwise collision detection that's used and the new quad tree that we implemented in this research. So in conclusion, MAMP is about getting robots to their goals without any collisions, and quad trees make the collision detection process much faster.